Hi everybody, welcome back to part 2 of the HP 5345A repair attempt and restoration. In the last video we have seen that I've been able to bring it back to life, but it's not counting, and we have no test function, internal checks doesn't work. So we just have all the displays having zeros, and the reset function just make the lamp test. So going ahead with attempt some troubleshooting, I've studied a bit the service manual, and this is the part of the overall block diagram. So the reason why I have this board out, which is A8, and it is the PLL board and the multiplier board, it's because using the internal reference, it multiplies the frequencies up to 100 megahertz in order to have a test signal. And it also, after that, multiply by 5 and gives 500 megahertz as a signal for the multiplexer. And as we can see on the next page, we have this gate gate section which receive the clock from this 500 megahertz signal. So I'm afraid that the frequency counter is frozen because it doesn't have the clock and the testing signal. As I have seen a lot of scratches, if you remember on the last video, onto the wiring here. So there might be that we have something wrong here. Now, unfortunately, onto the theory of operation, there is not much information on that, but on the adjustment section, I have all the levels, the signal levels that are required to be there. And it's over here. So I have various test points, so I should be able to check if my signal is there and the level, and see if we can start from a pulsing board as it should. I have a partial schematic in a very bad definition. And by the way, I'm able to read a bit. So the first thing that I want to check is the 10 megahertz input onto TP2 here, which is and TP1, and the output of this amplifier and buffering stage, which fed the multiplier section, which is over here. So let's check onto, maybe we can go directly onto TP14. We should have on TP14, as stated here, 20 megahertz. So let's do that. Now TP14, it's over here. Let's grab the oscilloscope. My probe is divided by 10, so we should have a 20 megahertz, and it is required about up to 2 volt peak to peak, and I'm having 237 millivolt. So I think we are there. It's a bit out of frequency because I believe we still have the overnighted reference over here that it's heating up. Oh, by the way, that is pretty stable once has warmed up, and it's also pretty precise, so that is not our problem. However, I'm seeing, yeah, it's jumping between 22 and 18 over here. So we are good here. Let's jump on to the next one, which is TP15, and we should have a nice 20 megahertz signal, which is right here. And yes, it is amplified. We are at 3 volt, more than 3 volt peak to peak. So over here, that is pretty nice. We are good so far. Sorry for the shaking, I'm just using my tripod to have hand free. Now on TP16 I should have a very low signal at 100 megahertz, so it should be 0.7 to 0.1 volt, so I'm expecting maybe 10 millivolt roundabout on TP16. Yeah, here we have about 12 millivolt 100 megahertz, which is fine, so we are good so far. And on to the schematic, we already are on TP16. We are here. So we have the next stage of this differential amplifier, which is TP17. Now TP17 is over here. We should have, as it's stated onto the adjustment section, from 0.6 to 0.7 peak to peak. So we should have 60 to 70 millivolt onto TP17, again 100 megahertz. TP17 is over here. We do not have our signal over here. That is bad. That is really bad. Now here there is this resistor R81 labeled RA, which is this one, and adjusting that from one end to another, I have no difference. So I'm afraid that we have a faulty IC over here. So let me check which kind of IC it is. It's labeled 1858 0004. So let's see the cross reference, what it says. Sorry guys, my fault. Actually TP17, that I taken was the ground, and the hot side was onto this point, and it's working perfectly. Look at this. We have 66 to 70 millivolt peak to peak, and remember my probe is divided by 10, so we have 700 millivolt. So that is completely working. At this point we have our 100 megahertz test signal. So we need to test the 500 megahertz, which is a bit more difficult to do. Okay then, my reference signals are all present. This is the last stage, 500 megahertz. Look how precise it is. That is unbelievable. By the way, this is not where the fault lies, so we need to go ahead and troubleshoot the counting section. Now, as our test signal is perfect, we need to go ahead onto A9, which is named 3-input multiplexer, and it is the beautiful gold-plated board. Okay, this is the A9 board onto the extenders. I already have checked for signals. It's quite complicated, so I had to figure out what's wrong in it. So these are the input selection ICs, those two, and they select the input signal from the preamplifier or test signal, which is this is missing 100 megahertz test signal, and it's fed onto this input and also onto the other as parallel. When the front panel switch is placed on check position, it is enabled the IC over here and gives the output. This IC is faulty, as was already seen from the previous owner. Unfortunately, on channel A is also faulty another IC, which is U4, and it is over here, which is a divider by 2. Channel A, it's faulty, I have no output, so I decided to swap with channel B, which is faulty the input, to have at least one good channel, and I've placed it here, and with this I have my good signal onto TP2, and I also have good signal at the output of the transistors. So now I want to check if I have those signals as good as need. By the way, this is divided by 10, and we have here we have 10 megahertz, 100 megahertz input. Here we have 50 megahertz, and here we have inverted and not inverted signal. So they are 180 degrees phase shifted 5 megahertz signal. I think here we have different frequencies, so I think it's interesting to see what we have there. Okay, here we have the instrument on check, still no count, by the way. This is the faulty IC on channel A, unfortunately. I'm monitoring the divide by 2 signal. Here we have 50 megahertz. And if I move onto this position, I have 10 megahertz, which is divided by 10. The next signal that I want to check is the output, which also drives the counting section. As you can see, I'm checking on TP1, which is divided by 10, and onto the output here we have divided by 20 actually, as we have 5 megahertz. So I think that on pin 1 and pin 14 there would be, as this is a scalar, different frequencies. Let's check those onto U9, pin 1 and 14. Oh, by the way, this is the output of the transistors, which I have 5 megahertz over here. not really visible. And 5 megahertz also to the other output over here. Yeah, so the IC seems to work fine. Now measure pin 1 and 14. Okay, on P14 we have a 25 megahertz signal. It's a bit dirty, but it's there. Not sure if it should be cleaner than that. But it seems that we have some signals, but the counter doesn't count. So on pin 1 we have 10 megahertz, which is pretty fine. So I think we need to go ahead onto the next board. Well, I have to admit that the troubleshooting on this counter, it's pretty a challenge, as it's not straightforward. The signals are going back and forth between the boards, and luckily I have board extenders, otherwise it would be a real nightmare. By the way, I decided a small different approach. I'm injecting 1 kilohertz signal as looking through the 100 megahertz test signal. It stretches my 100 megahertz oscilloscope. So I decided to went down of frequency. So luckily the input signal is correct, and all the passages are running. The selection here, it's functioning. So that is pretty good. But what I've discovered so far is that my gate is not running. So we have the gate control, which does not control the gate time. We only have gate in the minimum and 100 nanosecond gate time, which, by the way, it's not enough to make measurements. So I think I need to investigate that, and to do that this is what I've found so far. This is A9, and here we have our time gate, which is the gate that open and close and makes the count happen. That will enable the event to pass through the counting. Without that signal, we don't have that happening. Now, when I switch on to more appropriate range, gate lamp remain lit as it doesn't close anymore. Now, looking at this schematic, I've traced it to A10, which is the board that is exposed right now, which uses this circuitry to gives the gate arm signal, which in turn enable the gate onto A9. Now I have exposed the board onto the extenders, and I've noted this blown resistor, which seems to go to exactly maybe this or that, not really sure. So I think we have a small clue here. And looking at the board layout, it seems to be R63, which is the one close to the transistor, which is right, this one. So R63, let's see on the schematic. R63 it's sort of load onto the gate control, so probably from external control, and maybe somebody has feeded some wrong signal and has fried the resistor. So, by the way, let me check those components. Checking a little quick the resistor. It measures 1.5K and it should be 51 ohms. So this is fried for sure. And I was looking onto the schematic for R62, which is this one, and Q17 and Q16 on parts layout. Q17, Q16 and R62, which is also fried. There is pretty much evidences of burnishing, so I think it must be checked also that, which is also 51 ohms resistor. Let's check right now. That's still alive. Okay, I think it's a good idea to check also transistors. Well, Q17 measures fine, seems, but Q16, it's a bit weird. I think it's worth the removal, as it's going to influence this forced arm, so better to be sure over here. Alright, so the resistor is replaced. The transistors is measured both fine. I think they were influencing each other onto the circuit. Diodes measure fine, so at least in circuit we can go ahead and step back onto gate arm signal that we are losing when we are selecting certain gate time. But I'll say the signals are going back and forth, and indeed I have traced the loss of the signal to not arm from A11, which is the lowest board of this shorter board. So yeah, need to figure out why we lost our arm signal when we are going up in range. There is another point, by the way, which maybe could be a good clue to trace. When I change the range, I should see, and position, display position, I should see the decimal point moving, and perhaps also the length of the display should change. So there might be something also in the control that may prevent the functioning. To a certain extent it's working, as I've traced the scalar selection with range control, and it's working perfectly. So that part it's working, but it seems more onto the display control, but I could be wrong on that. So let's go back onto scalar board. Oh boy, how difficult is this instrument? Well, despite it is named as a microprocessor controlled instrument, it is actually done only by discrete components. And when I mean discrete ICs, so long story short, I don't want to bore you with the whole process I've done. But during the troubleshooting, which I also have used my logic analyzer, it seems that we don't have the whole amount of instructions that prompts should give to the instrument. But with my logic analyzer, I wouldn't be able to make any test. I don't know if because my logic analyzer went crazy. So what I decided to do is to try to find the prompts, which are of course pretty difficult. But I've been able to find another board, and the seller states that it has been tested and it is working. So I want to try to use the replacement board to see if I can give to the instrument more activities, as we don't have any decimal points, and by switching the range should moves, and with display position should also move the numbers of digits that are displayed. And it seems that all of those, it's done thanks to the instructions coming from prompts. So I really believe that we have a problem with some of those prompts, which, by the way, are SN74287, which are just a one-shot programmable ROM. I'll wrap this video right here, as I can't really go ahead with without the prompts on my hand. So I will skip to other projects. I have just received a nice signal generator, so another one. And I think in the next video I will go on that one. So I thank you very much for watching, and I'll be back very soon. Bye.